The last class we have studied about basic unit cells, no? So primitive unit cell, and we have studied its four properties. Then we have studied about BCC, body centered cubic cell, and as well as we have studied about FCC. This we have studied, no? Now we are studying about how to pack a crystal. Are you able to understand, ma? So packing can be of many types, no? First of all, we will study about one-dimensional packing. What is meant by packing, ma? Arrangement of cells is nothing but packing. Are you able to understand? So first of all, if I study about one-dimensional packing, what is meant by one-dimensional packing, ma? Packing along any one dimension. Okay. So that is either lengthwise or breadthwise or depthwise. Okay, ma? So along only one dimension, if I pack the atoms, then it is called as one-dimensional packing. And here two methods are possible. Clear, no, ma? So let us see method number 1 and let us see method number 2. Okay. So what is meant by method number 1? I can pack the atoms like this, no? Okay, ma? I can pack the atoms with a small separation between them. Okay. So atoms can be packed with small separation. And one more type of packing is that I can pack these atoms without any separation also, no, ma? So I can pack them like this also. Okay. So out of first method and second method, which is a desirable method, can you say? A method baguntundantaru. Second method is more desirable. Are you able to understand, ma? So therefore we write, so method 2 of packing without gaps, okay, ma, is more desirable. Why? Because, what is the reason, ma? Because we need to have maximum packing efficiency. Okay, ma? Always what is desirable, ma? Always maximum packing is desirable. Are you able to understand? So therefore, instead of packing like this, if this is the packed structure, then this one is more desirable, because in some space, in same amount of space, more atoms can be packed, no? So this is the more desirable quantity. Are you able to understand? So instead of this one is a more desirable quantity. So this is about one-dimensional packing. Okay. Next I study about 2D packing. Okay, ma? Now what is meant by two-dimensional packing, ma? Packing in two dimensions. Lengthwise also as well as breadthwise also. In length and breadth I should have atoms. Depthwise we are not discussing. If I go to depthwise also, it becomes a three-dimensional packing. We are studying only about two-dimensional packing. Clear, na, ma? First of all, let us take this array here. Okay, ma? So this is the array. Are you able to understand? So how I can pack these atoms? I can pack these atoms such that one atom is exactly below the other atom. So I can pack like this, no, ma? So this is one method of packing. Are you able to understand what is happening? One method of packing. Okay. So one atom is placed exactly below another atom. So like this you can place any number of groups or any number of columns. Are you able to understand? Now here one thing which you can observe is that, Klima, in this, in between these atoms, there are some empty spaces also, no? Are you able to understand? So let us see by one more color here. So which is the empty space present here? Okay. So this is the amount of empty space which is present, no? These empty spaces are present. So this is also an empty space. Are you able to understand? Clear? So these empty spaces, what we call them, ma? We call them as voids. Okay, ma? And can you say what is the shape of this void here? Shape of the void, you can call it as cubical void. Okay, ma? Or just if you want to say in only two dimensions, you can say it is a square type of void. Okay, ma? So this is the type of void which is existing here. This is one type of packing. Are you able to understand what is happening? Clear, no, ma? Similarly, similar method how I can pack. So this is the first method of packing. Okay, ma? First method. Now for example, if I take any one atom, okay, ma? let us take this atom, okay, let us take this atom to be my reference. This is my reference atom, okay. Now this reference atom, it is being surrounded by how many atoms? The atoms which are touching with each other. So how many atoms are touching this particular atom? Can you say? 4 atoms are touching, no? What are the 4 atoms? So first one, second one, third one and fourth one. 4 atoms, they are touching with each other. Are you able to understand? So therefore, if I draw a figure here, clear no ma? So what is the figure formed ma? Square. So that is why this type of packing we can call it as square closed packing. This type of packing square closed packing we call it, because the unit cell which is formed here, it is in the form of a square. Are you able to understand? So that is why what we call this one, this is called what? A square close packing. SCP, square closed packing. Rhombus. Did I say rhombus? Rhombus also you can call it, but rhombus means angles may not be exactly 90 degrees. Are you able to understand? And distances also may not be exactly same. But here, all the atoms, they are having same radius and angles is also exactly 90 degrees. No? So definitely you should call it as a square closed packing. So this is one method of packing. Are you able to understand? So in this condition, the packing efficiency will be approximately 78.5. In which type of packing? In square close packing efficiency will be how much? 0.785. Or you can say in terms of percentage, you can say it is 78.5. Are you able to understand? So right. So this topic we have to deal very slowly, otherwise you can never understand what is happening here. Okay? So so in square close packing, okay okay. So see the packing efficiency of square close packing is how much? 52.4. And I will try to calculate its calculations, okay. So this is one type of packing, So what is happening here? Below one cell I am placing one cell, and in between 4 cells you are finding a void. And what is the shape of the void, You can call it as cubical void, or you can call it as a square type of void. Clear, no? So now let us see the second method of packing. Second method of packing the atoms in 2D space. Okay. So first of all, let us take one atom in one dimension. Okay. Now see, second type of packing is that I can place atoms here also, no? I can place like this also, no? Are you able to understand, no? So this is the second type of packing. I can place atoms here also. So, okay, approximately like this. So very carefully we have to draw the diagrams, otherwise horrible figures you will get. Okay. I think intakanna ghoram chestaru meeru. I am better, I think. Are you able to understand? So this is the second type of packing which I can pack the atoms in 2-dimensional space. Okay, ma? So now see here, atoms, they are present only lengthwise, and atoms, they are present only in breadthwise. Only 2 types of arrangements. Either I can place atoms like this, or I can place atoms like this. Are you able to understand? Now let us see the arrangement of voids in this condition. So where voids are present here? So this is one void, no? Okay, ma? And this is another void. This is another one. So this is another one. This is another void. This is another void. Okay. Now can you say what is the arrangement of these voids? So voids ela arrange ayunnai cheppandi. Okay. So voids if I draw here, so voids will be somewhat like this. Okay. This is pretty diagram lo nenu chuste antene Mike. Okay. So this is the second type of arrangement, and these are the voids. So one void is above the reference and one void is below the reference. Now can you say what is the shape of these voids? Triangular shape. So shape of voids is, okay, ma? So triangular shape. This is the shape of the voids. Okay. And what is its packing efficiency or packing fraction? How much might is 60.4%. This is the packing efficiency of this two-dimensional arrangement of these atoms, where atoms are arranged lengthwise as well as breadthwise. Are you able to understand? Okay. So make a note up to here. See ma, one more point here. For example, if I take this atom to be the reference atom. Okay ma? Red color is there. Okay ma? So if I take this atom to be my atom of reference atom, then can you say how many atoms are surrounded by this atom? 6, no? So how many? So this is one atom, so this is second atom, so this is third one, this is fourth one, this is fifth one, and this is the sixth one. Are you able to understand? So totally 6 atoms are being arranged here. Are you able to understand? Now if I draw the figure here, let us see how I can draw the figure ma. So this is the line which is joining these two centers. Clear no ma? And this is the line which is joining the centers of these two atoms. Now these two, they are joined like this, and these two, they are joined like this. Okay ma? These two atoms are arranged like this, and these two atoms, they are arranged like this. Okay. So what is the type of unit cell which is formed here ma? Hexagonal shape. Okay. So in this type of arrangement, the type of shape was square, but here the type of shape is what? Hexagonal. So therefore this is called as what kind of arrangement? So this type of packing, is called, okay ma? So hexagonal closed packing. Are you able to understand? Where each atom is surrounded by 6 other similar atoms. Understood no? So therefore in 2D packing, totally how many types of packing we have? One is a square closed packing, another one is hexagonal closed packing. So therefore you can draw like this. So 2D packing, you can divide this one into 2 types. So first one is square closed packing. Okay ma? And the next one is hexagonal closed packing. Okay. So here what is the type of void which is present? Cubical voids, or you can call it as square voids. So this is the type of void present here. And what is the packing efficiency ma? Packing efficiency is equals to 52.4%. Clear ma? And in the case of hexagonal packing, what is the type of voids we have? Triangular voids are present. Okay ma? And what is their packing efficiency? Packing fraction is equals to 60.4% is the packing efficiency. Okay. So make a note up to here. Then we will study about 3D. Okay. See ma. So 3-dimensional packing. In 3-dimensional packing means what? Here atoms are present along lengthwise also, they are present along breadthwise also, they are present along depthwise also. In all the 3 dimensions you can find that. That is called as 3-dimensional packing. Okay ma? So in 3-dimensional packing, again we have 2 types. What are they? We can pack square closed packing also. We can use this one in 2D dimension. Similarly, we can also use hexagonal closed packing also. Again in 2D. Okay ma? So we can use these 2. So we can use a square closed packing also for packing in 3 dimensions. Similarly, I can use hexagonal closed packing also for packing in 3 dimensions. So first of all, let us study about first one, which is called as square closed packing. Okay ma? Let us see how we can convert this square closed packing in 2 dimensions into 3 dimensions. Square closed packing we have studied in 2 dimensions. No? That one I want to convert into 3 dimensions. And how many different methods are there? Let us see. Okay. First of all, let us draw this figure. Drawing the figure is the biggest challenge here. Okay ma? So ఈ క్లాస్ కోసం 2 మార్కర్లు కూడా కొనుక్కొనొచ్చునా నేను. Okay. So this is a square closed packing no ma? Square closed packing. Are you able to understand? So therefore, which type of voids are present here? Cube type of voids, or you can call it as square type of voids are present. Are you able to understand now? Now in this square closed packing, first of all we will discuss about the first method. Okay ma? First method. Which is the first method? First method is, see ma. So on this atom I can place one more atom, no? On the same atom I can place one more atom. How I can place? See ma, here black color indicates what? Black color indicates first layer. Okay, this is the first layer of atoms which are arranged in 2 dimensions. So on this one now I am going to arrange second layer also. దీనిపైన ఇంకొక layer arrange చేస్తా ఉన్నాను. Okay, and that I will represent by red colored layer. Okay, so therefore what does red color indicate? Second layer. So how I can arrange atoms? No, this is one layer, no? Above this one I will place another layer. So I am placing atoms like this. Are you able to understand? On the black colored atoms I am placing red colored atoms, but don't think atoms have any color. Just for your understanding I am saying. So this is second layer which I have placed. This is one type of pattern. Okay ma? One layer, on that one there is one more layer. Black colored atoms, they are forming one layer in 2 dimensions. On that one we are placing one more layer of red color atoms. Are you able to understand ma? So it automatically converted into 3-dimensional figure, no? Okay. Previously it was having length and it was having breadth also. Now it has a thickness also, no? Because on one atom we are placing one more atom. Are you able to understand ma? And this type of packing we can call it as A packing. This is the name of this packing. Okay. What is meant by A packing? Okay. First layer is black color, no? First layer is black color. Second layer is red color. But arrangement is same type of arrangement, no? So the type of layer has not changed here. Type of layer has not changed. That is why this type of layer I can call it as A. On that one you place third layer. On that one you place fourth layer. On that one you place the fifth layer. Type of layers, they are not changing. That is why we call this packing as A packing. Are you able to understand? No? So this is one type of packing. Okay. So right. Clear? So therefore, chala careful ga vinandi. If you don't understand these basics, you cannot understand the higher figures. So therefore what we write here, we write that the type of layers placed one over the other is not changing. Okay. So that is why it is called as A layer. Any number of layers you can place. Are you able to understand ma? So one layer of black, one layer of red, one layer of green, any number of layers you can place. Okay. And what is the shape of the void? In 2 dimensions, if you say the shape of the void is remaining to be square shape, or you can call it as tetrahedral shape also. If many layers you can place, then the same void it converts into tetrahedral shape. Are you able to understand ma? That's it. Okay. So any other point here I have to discuss? Here, note point, very important note point you can make here. Note point is that, so the type of unit cell in 3 dimensions formed will be PCC. So this is the most important point. Are you able to understand? So if we are placing this type of arrangement, then the unit cell which is formed in 3 dimensions, what will be the type of unit cell ma? Type of unit cell will be PCC. What is PCC? Primitive cubic cell. Are you able to understand ma? And what is meant by primitive cubic cell? Atoms, they are present only at the corners. Atoms are not present at the center also. Atoms, they are not present at the face also. They are not present at the edges also. So if this type of arrangement we are placing, then the type of unit cell formed is PCC. And what is the packing fraction of PCC ma? Packing fraction of PCC is how much? 52%. Okay ma? So packing fraction of 3D unit cell is how much? It is 52%. Why it is 52%? Because here the type of unit cell formed is PCC only. No? Are you able to understand? No? So this is one kind of packing. So then we study about the second method of packing in the same square closed packing. Clear now? Completed up to here? Okay. So second method of packing in what? In square closed packing. Are you able to understand now? Which is the second method? Let us see. So first of all, let us draw the square closed 2D figure. So maintain the size of the atoms, then very easily you can draw the figure. So this is a square closed packing now. Each atom surrounded by 4 atoms. Now see. So again we draw the layers here. Black color layer indicates first layer of atoms, and red color indicates second layer. Okay, ma'am? And in this condition, how I can place this second layer is that I can place the second layer such that these voids, they are completely filled. Okay, ma'am? In the first case, on one atom we were placing second atom, no? Now in this condition, what we are doing, we are placing the atoms such that voids are covered. So this is one void which is present, no? So cover that void by an atom. So this is one type of arrangement. Okay, ma'am? And this is the second void, so this is the second atom. This is the third void, so this is my third atom. Okay, ma'am? So like this, if you are able to cover the voids, okay, then this type of arrangement is the second type of arrangement. Okay, ma'am? First layer is made up of black atoms, second layer it is made up of red atoms. Are you able to understand how we are packing? Are you able to understand? So what is the method we have used here? Method is that, so second layer is placed such that voids are covered. Okay, ma'am? Voids are covered in this condition. So this is the second type of arrangement in which type of packing? Square closed packing. In 2D packing we have two types of packing, no? One is square closed, second one is hexagonal. And again in a square closed packing we are studying two methods of 3D packing. One is atom placing on the same atom. Second one is atom placed on the only voids itself. Are you able to understand, ma'am? Therefore, the important note point here, what I have to write is that, okay, ma'am? Important note point is, right now, okay? So here, the type of unit cell formed is BCC, body centered cubic cell. Are you able to understand, ma'am? So when you are placing the atoms such that it is covering the voids, okay, then what is the type of unit cell formed here? The type of unit cell formed is BCC. Previously it was PCC, primitive unit cell, but here it is a BCC. What is meant by BCC, do you remember? Body centered. What is meant by BCC? No, atoms, they are present at the corners. At 8 corners atoms are there. Similarly, there is one atom exactly at the center of the unit cell. So that is called as BCC. No? And what is the packing efficiency of BCC, ma? 60? 64, I don't think. Packing fraction of BCC unit cell is how much, ma? 68%. So therefore, if this type of packing is done, then you can form a BCC. And whose packing efficiency is how much? Packing efficiency is 68%. Okay, ma? So if packing efficiency is 68%, what is the void space? Void space is equals to 32%. Already we have studied, no? So this is the method of constructing a BCC, body centered cubic cell. Okay, ma? Place one layer of 2D atoms in square closed packing, and you fill the voids with atoms. Then automatically you will get a 3D space in which BCC atoms you can find, BCC unit cells you can find. Are you able to understand, ma'am? Okay. So next we take the hexagonal closed packing, and in that also we will study some types of packing. Okay, ma'am? So right. So what is the second type of packing? Second one is hexagonal Now see, so next we are studying about hexagonal 3D packing, how to do 3D packing with the help of hexagonal close packing. Are you able to understand, ma? Now see here, what is the shape of the voids which we saw, ma? So here there is one void, no? Marker zero. Kaduna. Okay. So here you see one void, no, ma? And what is the shape of this void? Triangular void in the form of a triangle. Here also you see one void, no? So this is also a triangular void, and this is another triangular void. Okay, and this is also another triangular void. So what you understand? For example, if I draw a reference line, clear, Nama? So if I draw a reference line, so that is if I draw an imaginary line like this, clear? Then what will be the shape of the voids which are created? This will be the approximate shape of voids, Nama. This will be the approximate shape of the voids. Are you able to understand? So in the first layer of hexagonal packing, this is only first layer only, no? So atoms, they are arranged lengthwise, and atoms, they are arranged breadthwise, two-dimensional packing. But how many layers are there? Only one layer is present. Are you able to understand? So in that layer, you will get this type of voids. All the voids, they are triangular voids. Are you able to understand, ma? Now the point is that we have two methods of packing. Two methods of packing. Now this 2D figure, I can convert into 3D figure in two methods. What is the first method, ma? First method is close the upper triangular void. Okay, ma? Then lower triangular void cannot be closed. Cannot be closed. This is one method. Okay, ma? And second method is exactly opposite to first one. Exactly opposite to first one. Are you able to understand, ma? So can you say what is the meaning of the statement which I have written, ma? Ikkada em rasnanu cheppandi chuddam. What did I write? See, ma, here I am getting triangular voids, no? One void is above the reference line and one void is below the reference line. So now see here, one method of closing is I can close this triangular void by an atom. Are you able to understand, ma? Then the bottom triangular void cannot be closed. This is one method. And the second method is, if you try to close the lower triangular void, then upper triangular void cannot be closed. Are you able to understand what is happening? So either you can close either the upper one or the lower one. So these are the two methods of packing. Okay. Now I will do one thing. I will place one atom on the upper triangular voids continuously. Okay. Now so let us see how I can pack this one. Clear, ma? So I can pack it like this. So this is the method in which I can pack. Okay. Now here, what is the meaning of black color atoms, ma? Black color atoms indicates first layer. Okay, ma? And red color atoms, come on. Red color atoms indicates second layer of packing. Okay. And in second layer, how I am packing again? I am packing only the upper triangular voids. Lower triangular voids cannot be packed. They cannot be covered. Are you able to understand? Now see. Similarly, I will close this second one also. How can I close? Let us see. Okay, ma? So this one I can close like this. Are you able to understand? Okay. And the next, this void, how can I close? Let us see. Okay, ma? And the next upper triangular void, I can close like this. Are you able to understand? All the black color atoms, they are forming the first layer, and all the red color atoms are formed the second layer. And we are closing which voids? We have two voids, no? So there is one triangular void above the reference line, and there is one triangular void below the reference line also. So which triangular void I am closing? I am closing the upper one. You can close the down one also. That is your wish. Are you able to understand, ma? Okay. Now see here, this void which was covered, this void was covered, no, ma? This void will take the shape of, okay, ma? Closed. I think it will not be visible, ma? So see, ma, here, the void which is closed by an atom, this becomes closed tetrahedral void. It becomes closed tetrahedral void. Are you able to understand, ma? Winner. First listen very, very carefully. So here, one void I am closing, but one void I am not able to close, no? The void which is closed, that void will take which shape? That void will take the shape of closed tetrahedral void. Are you able to understand, ma? And the void which I was not able to close. So this is that void which I was not able to close, no? This void and this void. they will take the shape of, okay ma, open octahedral voids. Okay ma, they will take which shape? They will take the shape of open octahedral voids. Are you able to understand? So మీరు క్లోజ్ చేసిన void ఉంది కదా, that will take which shape? That will take the shape of closed tetrahedral void, because it is closed on one side. It is closed on top side also, it is closed on bottom side also. That is why it is called as a closed tetrahedral void. And the void which you are not able to close. Now see, in this void, this first atom also has taken some region. Second atom also has taken some region. Similarly, bottom atom also will take some region. So therefore, it will take which shape? It will take the shape of open octahedral void. Now there is no atom placed on this one. No, that is why it is open octahedral void. Are you able to understand, ma? Let us draw one more layer, some more atoms in this second layer, ma. So now see. Now here, can you say which are the voids which I have to close and which are the voids which I cannot close, ma? So this void and this void, they are above the reference, no? So those voids should be closed. So listen very, very carefully, ma. And what about this layer? This void is present below the reference, no? So this void cannot be closed. Are you able to understand? So how to close this one? So I will close this one like this. Clear, no? Similarly, this void also should be closed, but this void cannot be closed completely. So therefore, the shape of the atom which I will draw is like this. Are you able to understand? Okay. So therefore, what about this void? What is the shape of this void, ma? Chappan tondarga, huh? Closed tetrahedral void, because it is already closed, no? Now what about the void created here? This will become the shape of open octahedral void. This is what is happening. Are you able to understand? And once you see here, here also there is one more void which is created, no? This void. What about this void? Is it present in the first layer or is it present in the second layer? This one. This void is present between red color atoms, no? Ee void ekkadundi? It is present in between red color atoms. It means this void is present in the second layer. Okay, ma? And the shape of that void will be, it is called as open tetrahedral void. Are you able to understand, ma, what is happening? So we are discussing about 3 voids here. One void is a closed tetrahedral void, another void is open tetrahedral void, and the third void is open octahedral void. Are you able to understand? Now can you say where this, we will revise once again. Where is this open octahedral void present, ma? It is present in the second open octahedral void. It is present in the first layer, in between first layer and second layer, and it is that void which is not covered by an atom. Understood, no? And what about a closed tetrahedral void? It is the void which is present in between first layer and second layer, but it is covered by an atom. Are you able to understand? Then what about open tetrahedral void? It is the void which is present in the second layer, and where this red color, the gaps between red color atoms is nothing but open octahedral void. Are you able to understand? So make a note of that point. Clear, ma? So if a void in first layer, okay, ma, is covered by, is which void? Triangular void. If triangular void in first layer is covered by atom, then which kind of void will be created? Then closed tetrahedral void will be formed. Are you able to understand, ma? Void will be formed. Okay. Then if a triangular void in first layer is not covered, it converts into what, ma? It converts into open octahedral void. Open octahedral void. Understood, no? And the void in the second layer, is will be which type of layer, ma? Will be open octahedral layer. Open octahedral voids. So understood, nama? Which type of void is formed by closing one void? You are able to understand, no? So these are the 3 types of voids which are formed by forming the second layer. Are you able to understand? Okay. Completed, ma, up to here? Brian, make a note up to there. So one more point which I can write is, make a note point. One note point is that, okay, so for every n atoms of second layer, okay ma, so 2n which voids, 2n tetrahedral voids, okay ma, and n octahedral voids will be formed. Are you able to understand ma? So if you are placing n atoms in the second layer, then how many tetrahedral voids can be formed ma? 2n tetrahedral voids can be formed. It means double number of tetrahedral voids. And in this tetrahedral voids, one n will be open and one n will be closed. Clear no? And how many octahedral voids will be formed? N octahedral voids will be formed. Are you able to understand? So this is a point which you should understand. Okay? Completed ma? Yeah, no, see ma. So therefore, in this, after forming second layer, and which is the second layer, red color atoms, they will form the second layer. Okay ma? So after forming the second layers, we have discussed about 3 types of voids. No? One is open tetrahedral, second one is closed tetrahedral, and the third one is open octahedral. So in the name only you can see no, closed tetrahedral, it means it is already closed. Now how many voids are there for closing? 2 voids are available for closing. Are you able to understand? Now see. So therefore I am rubbing all of this. So in 3 types of voids formed, okay ma? In 3 types of voids formed, closed tetrahedral void is already closed. Okay ma? So it means on this void already we have placed an atom. So this is already closed. Okay? We have 2 voids that can be closed. Okay ma? Now what are the 2 voids by which I can close those voids by placing atoms ma? 2 voids are there. What are the 2 voids? One is this one. Which is this one? Open octahedral void. And the second one is open tetrahedral void. So these 2 voids are available for closing. Are you able to understand? Now see. So first one, placing third layer. Okay ma? Placing, I think not visible. Placing third layer on open tetrahedral void. Okay ma? Open tetrahedral void. Now there are 2 methods in which I can place the third layer no ma? 2 methods. What are the 2 methods? Either I can place the third layer on open tetrahedral void or I can place on open octahedral void. 2 methods are there. Okay. So we are discussing about the first method. Now 2 layers already I have placed no ma? Now I want to place the third layer. Okay. So where is the third layer? Sima, I want to close this void. No? What is this void? Open tetrahedral void. Placing third layer on open tetrahedral void. Okay ma? And the third layer I will represent by green color. Third layer represented by green color. Are you able to understand ma? So if I want to close this void, so this is the atom which I have to place. Are you able to understand ma? It means on the black atom only I am circling this green color pen no ma? On the black atom only I am circling the green color pen. So what do you understand? If I want to close this void, which is open tetrahedral void, again I have to place a third layer. And third layer is exactly symmetrically placed on which layer? It is symmetrically placed on black atom, which is the first layer. Are you able to understand ma? It means that in the third layer, first layer is again repeated, no? Arthamatunda? I want to close which void? I want to close open tetrahedral void. It means I want to close this void. If I want to close this void, I will place a green color atom. Don't think atoms are green, just for your information. Okay, ma? I am supposed to place a green color atom. And that green color atom, symmetrically, it is placed on which layer? Exactly, it is placed on first layer, no? Are you able to understand, ma? So therefore, what happens is, here, okay, ma? First layer is again repeated. First layer is again repeated. That is what will happen, no? Okay, ma? So therefore, type of layers will be A, B, A, B, A, and it goes on like this. Okay? Can you say why I have written A, B, A, B, A, B, ma? A is the first layer. B is the second layer. In the third layer, again it is repeated, no? So again layer will come. So that is why the type of layers created will be A, B, again A, B, again A, B, like this. Are you able to understand, ma? And here, the type of unit cell formed is, okay, ma? Hexagonal unit cell. This is the most important point. Are you able to understand, ma? So here, what is the type of unit cell formed by placing this third layer, ma? Hexagonal unit cell will be created. Okay, ma? Hexagonal unit length means it will have how many sides? 6 sides will be there. Previously we studied only cubic, no? Cubic means it will have a different construction is there for cubic. Okay, so how many faces? Totally 6 faces will be there. Are you able to understand, ma? And 12 edges will be present. But here the type of unit cell created is called as hexagonal unit cell. So you can call it as HCP also. Are you able to understand, ma? So this is the type of unit cell created in which condition, ma? When atom is placed where? Third layer where you are placing? Third layer you are placing on open tetrahedral void. That is the condition. Understood, no? Come on, make a note up to here. Okay, now see, ma. So there were 2 methods of closing the 2 voids, no, ma? First method of placing the third layer was placing atoms on open tetrahedral void. Then the type of unit cell formed was what? Hexagonal unit cell. And what is the second method of closing the same, which void now I have to close, ma? I have to close open octahedral void, I have to close. Are you able to understand? Now see. So placing third layer on open octahedral void. Okay, ma? Open octahedral void. Now where is octahedral void? Here there is an octahedral void, no, ma? This is an octahedral void, no? Are you able to understand? Let us close this one. And fourth layer, again I am representing by black color atoms, ma, because I have only 3 pens only. Clear, ma? So black I am representing by third layer only. Okay, this is one method of placing the third layer. Now we are discussing second method of placing the third layer. Are you able to understand, ma? Now this atom where I can place, I have to close this open tetrahedral void. This void I have to close, no, ma? Now let us see how can I close this one. Okay, so this is the method in which I can close this open octahedral void. Okay, now can you see any layer, is it repeated, ma? First layer, second layer, is any layer repeated here? No layer is repeated. Are you able to understand, ma? So that is the first point we have to write. So here layer is not repeated. Okay, ma? Layer repeatable. It means that new layer is formed. New layer is formed. Are you able to understand, ma? So therefore this type of arrangement is called what? This type of arrangement, what you call, ma? This type of arrangement you will call ABC type of arrangement. Okay. Now can you say what is meant by ABC type of arrangement, ma? First layer is A, the layer of black color atoms. Second layer is B, the layer of red color atoms. Third layer is C, or you can say another, again black color only is repeating, but it is not equal to first layer. Okay, ma? See, ma, this third layer, it is not placed either an atom of first layer or an atom of second layer. It is completely a new layer. Are you able to understand? That is why it is called as ABC. After that again A will repeat. After that again B. After that again C will repeat. So this is the type of arrangement. Are you able to understand, ma? And here the unit cell formed is, okay, ma? Here the type of unit cell formed is, okay, which type of unit cell is created here? FCC, face centered cubic unit cell will be formed in this condition. Are you able to understand? So if you are placing atoms on open tetrahedral void, what is the type of unit cell created? Hexagonal unit cell is created. But when you are placing atoms on open tetrahedral void, then what is the type of unit cell created, ma? FCC. And what is meant by FCC, can you say? Atoms, they are present at the corners, and there is an atom exactly present at the center of each face also. That is called as an FCC. Are you able to understand? So this completes our topic, which is called as packing of crystal in 1 dimension, 2 dimension and 3 dimension. Are you able to understand ma? Make a note up to here. అర్థమవుతుంది కదా ఏ atom ఎక్కడ ప్లేస్ చేసి ఓకే మా. So now we will have discussion on voids ma. How many voids will be there? What is the position of the voids? Okay ma. All this we will discuss here. Okay. So types of voids, how many types of voids we have studied? Triangular voids, tetrahedral voids, octahedral voids and cubical voids. These are the type of voids which we have studied. So where a triangular void will be created ma? Position, can you say? Position is triangular void. So in the first layer of hexagonal close packing in 2D. This is the position, no? Do you remember? When atoms, when they are placed in 2D dimension, and in which type of arrangement? Hexagonal close packing. Then what was the type of void I got? Then the type of void which I got was triangular void. Are you able to understand ma? Okay. So the radius of atom that can be placed on void is given by radius of void is equals to 0.155 radius of the atom. So this is a very, very important discussion. So if I want to close that void, which void ma? Triangular void. Are you able to understand? Then RV means what? Radius of atom placed on void. What is the radius of the atom that should be placed on the void to close that void? And it is equals to how much? 0.155 times of radius of the atom. What is meant by radius of the atom? Original atoms by which this void was created. Are you able to understand ma? So see ma, one more discussion I can write here. Same RV can be written as R plus also. I can call it as a cation also. And this is equals to 0.155 times of radius of anion. Okay. So why I am calling the radius of the atom which can be placed on the void to be a cation ma? So I want to close which void? I want to close triangular void. Then what is the radius of atom I have to place? This one. RV is equals to 0.155 times of RA. What is RA? Radius of original atoms by which triangular void was formed. Are you able to understand? Or if you want to draw a figure, Sima. So this is RA, radius of the original atom. Okay. And in hexagonal packing, here I will get a triangular void, no ma? So on that triangular void, what can be the radius of the atom I have to place? This is the radius of the atom I have to place. Okay. And that radius is given by RV. And this is the RV. Arthamatunda? Atom placed on void. Are you able to understand? And what is its value? Radius of the atom which can be placed on the void is how much? 0.155 times of radius of the atom by which this triangular void has been created. That is the meaning of it. Arthamathundi kada? And these values also there is some calculation ma, but we don't go for calculation, just by heart these values. Okay. Now see, listen carefully. So the size of the atom or radius of the atom which can be placed on the void, I have represented it by R plus, radius of the cation. Why? Why is it like that? Because it is very smaller in size, no ma? When compared to radius of the atom which is creating this void, the radius of the atom placed on the void is very small. And generally cation sizes will be very small, no? In periodic classification we have studied, no ma? What is meant by cation? The atom, when it loses electron, it will become positively charged. And what happens to its size? Increases or decreases? Decreases. Why size decreases, ma? Because the net force of nucleus on the remaining electrons increases. And automatically size will decrease. Or in another method, how can I say? Once it has lost an electron, it doesn't want to lose another electron, so it will reduce its size. Are you able to understand? So point is that radius of the atom which can be placed on the void, it is smaller, no? So that is why it is represented by R plus. And the radius of the atom by which this triangular void is created, that is represented by anion, R minus, because it is bigger in size. Is it clear? That's it. Now let us have a discussion on tetrahedral voids. Okay ma? Where tetrahedral voids were created ma? Okay. So position we will discuss. Position. Where is the position? Okay, ma. So closed tetrahedral voids were created because of second layer in HCP, hexagonal close packing. Already we have discussed, no? Triangular voids, if you close them by an atom, then what is the type of void created? Closed tetrahedral void. That is the void which is created, no? Are you able to understand? And open tetrahedral void. Open tetrahedral void was present where? Was present in second layer of HCP atoms. Do you remember? Red color layers we have drawn, no? In between that red color layers only we were seeing this open tetrahedral void. That is the position of tetrahedral voids. Okay, ma? Open tetrahedral as well as closed tetrahedral voids. Okay. And here, where these tetrahedral voids they are present inside the unit cell, that also we will write. Okay, ma? So tetrahedral voids are present at a distance of d by 4 on the body diagonal from corner. Okay, ma? So this is the arrangement of tetrahedral voids, and this position you are supposed to by heart, because if you try to understand, I don't think it is possible. Are you able to understand, ma? So where tetrahedral voids they are present, ma? Tetrahedral voids they are present at a distance of d by 4 on body diagonal. How many body diagonals will be there for a unit cell? Body diagonals are not 4 body diagonals will be there. Okay, ma? Each body diagonal will have 2 tetrahedral voids. At what a distance? At a distance of d by 4 from the corner. Okay? I will do one thing, ma. I will draw the figure here. So you write below this one. I have no space now. I am writing here. So therefore, consider this is a unit cell, cubical unit cell. Are you able to understand, ma? So totally how many body diagonals will be there, ma? So this is one body diagonal, and this is one body diagonal. Clear, no, ma? And this is one body diagonal, and this is one body diagonal. So 4 body diagonals will be possible. Are you able to understand? And where is its position? Position is here. Here there is one tetrahedral void, and here also there is one tetrahedral void. And what is this distance? This distance is d by 4. Okay, ma? And each body diagonal will have 2 tetrahedral voids. Are you able to understand? How many body diagonals are present? 4 body diagonals will be there. Each body diagonal will have how many tetrahedral voids? 2. So total tetrahedral voids? 8. 8 tetrahedral voids will be present. Are you able to understand, ma? So make a note of it. So this is the position of tetrahedral voids, ma. Are you able to understand? So write down. So each body diagonal will have 2 tetrahedral voids. Okay? Total how many body diagonals? 4 body diagonals. Clear, no? Therefore, total tetrahedral voids are how many? 4 2s are 8. And this is in which case, ma? This is in the case of FCC, face-centered cubic unit cell. Okay? So in FCC, how many tetrahedral voids will be present? 8 tetrahedral voids will be present. Are you able to understand? And there is a relation between HCP and FCC. So this is the relation. So hexagonal unit cell, or you can call it as hexagonal closed packing, this is equals to 3 by 2 times of FCC. Therefore, number of voids in hexagonal unit cell. And you should remember when this hexagonal unit cell was formed. Hexagonal unit cell eppudu form ayindi? Cheppandi. When open tetrahedral void was closed, then you got this hexagonal unit cell. So number of voids in hexagonal unit cell is how much? 3 by 2 times of FCC. Clear, nama? 3 by 2 times of how many tetrahedral voids are present in FCC? 8. So 3 by 2 into 8 is how much, ma? 12. So 12 tetrahedral voids are present in which type of unit cell? Hexagonal unit cell. Okay? And how we got this relation, you need not understand, you have to by heart it. Understood, Nama? That is the discussion. Arthamavutundi kada? Make a note up to here. Okay, ma? Now see the positioning and number of voids which can be possible in which kind of voids? In octahedral voids. Now can you say how they are formed, ma? Formation. How they are formed? Come on. When second layer of HCP was not covering triangular voids. Okay, ma? So two types of arrangement we have studied. No? Either we can close the top triangular voids or bottom triangular voids. When top triangular voids was created, bottom triangular void it has converted into octahedral void. This is the arrangement of octahedral void. Are you able to understand, ma? And so here I think I have forgot one point. Point is that, write down. In tetrahedral void, radius of atom which can be placed on the void. What is meant by RV, ma? RV means what? Radius of atom which can be placed on the tetrahedral void. This is equals to 0.225 RA. Okay? What is meant by RV, ma? Radius of atom that can be placed where? That can be placed on tetrahedral void. Okay? And what is meant by RA? Radius of that atom which created this void. Difference arthamavutundi kada? Or in terms of cation and anion you can write R plus is equals to 0.225 or minus. So you can write like this also. Okay? Because in a crystal, if one is a cation, another one should be anion. Are you able to understand, ma? That's it. So now see, octahedral voids. When second layer of HCP was formed, was not covering triangular voids, then this octahedral void was created. Okay? Now where is its position? Position is, it is present at the center of edges. It is present at the center of edges and exactly at the center of unit cell. Are you able to understand? Okay, ma? Now see, ma. Here one more discussion we have to do here in tetrahedral voids. See, ma. So totally how many tetrahedral voids are present in FCC, ma? 8 tetrahedral voids are present, no? And all of them they are present inside the unit cell, no? All these 8 tetrahedral voids, where they are present? Inside the unit cell. So therefore what is their contribution? How much percent will be the contribution? 1/4, 1/2, 3/4, how much? 1/8. Contribution will be 100%. Contribution will be 1. What is the reason? Because these voids, they are completely present inside the unit cell, no? Okay, ma? For example, if an atom is present at the corner, then this atom can be shared by how many unit cells? 8 unit cells. That's what we have studied, no? If there is an atom present on the corner, then this atom can be shared by how many unit cells? 8 unit cells. So this therefore contribution was only 1/8. That was what we have discussed in the first class, no? Okay. But these voids, tetrahedral voids, where they are present? They are present inside the unit cell. So therefore total void is present inside only, no? So contribution will be how much? 100%. So you can make a note of that point here. Clear, ma? So below this one, make a note point. What is the note point I have to write? All tetrahedral voids are present, okay, ma? Where? Present inside the cell. Okay? Therefore, their contribution is how much? Their contribution is 100%. Okay? So if 8 tetrahedral voids are present, all the 8 will be there inside the unit cell. If 12 tetrahedral voids are present in HCP, all 12 will be present inside the unit cell. Are you able to understand? But here the discussion is quite different. Now see. So where is the position of octahedral voids, ma? It is present at the center of edges and exactly at the center of the unit cell. Let us draw the diagram first. Make a note of this point. Completed, ma? Now see. Now by looking at this statement, can you say what is the meaning of this one, ma? Ekkadu night octahedral voids cheppandi. Where is the position of octahedral voids, ma? So I will draw the unit cell. So this is the unit cell which is created. Clear, Nama? So octahedral voids, they are present at center of edges. Which is an edge here? This is one edge, Nama. Clear? So like this, how many edges will be present? How many edges will be present in a cube? Edges. 12 edges will be present. Are you able to understand, Ma? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges will be present. Okay? So 12 octahedral voids will be present on that particular unit cell. Are you able to understand? And one more location is that. What is that one more location? Exactly at the center of the unit cell, one octahedral void will be present. So exactly at the center of this, what you call unit cell, one octahedral void will be present. Okay? So therefore, now can you say, what is the contribution of the void which is present on the edge? If there is a void present on the edge lo unte, then how much void will be present in one unit cell? Oka unit cell lo enta contribution untundi? 1 by 4. 1 by 4 already we have studied, no? When atoms, when they are present at the edges, that edge can be surrounded by 4 atoms, 4 unit cells. Okay? So therefore, totally how many edges are there, ma? So totally 12 edges. Okay, ma? And contribution is 1 by 4. Therefore, octahedral voids on edges. Total will be how much, ma? It will be 1 by 4th of 12. 1 by 4th of 12 is how much? 3. That is the meaning of this one. No? It means this unit cell will comprise, totally it will accommodate how many octahedral voids? 3 octahedral voids. Are you able to understand? Okay, ma? And there is one void exactly at the center, no? And what will be its contribution? 100, because it is totally present inside, no? So 3 plus 1? 4. So 4 is the number of octahedral voids that can be comprised of FCC, face-centered cubic unit cell. Clear, Nama? So write down. And contribution of octahedral void at center is how much? 100%. Therefore, total number of octahedral voids will be how many? Okay, ma? Therefore, total number of octahedral voids is how much? 3 plus 1, it is equal to 4. And this is the value in FCC, face-centered cubic unit cell. Okay, ma? If it is the value in FCC, then what will the value in HCP? HCP, what is the relation we have written? HCP is equals to 3 by 2 times of FCC. So 3 by 2 into 4 is how much, ma? 6. So therefore, in hexagonal unit cell or hexagonal close packing, how many octahedral voids will be present? 6 octahedral voids will be present. Are you able to understand, ma? So this is the easiest method of remembering the number of voids which are present in different locations. Okay? Time on the అయిపోయిందా? ఎంత ఎక్స్ట్రా అయిపోయిందా? క్యూబికల్ వైడ్స్ ఒకటి చెప్పేద్దామా? వద్దులేండి, రేపు డిస్కస్ చేద్దాం. ఓకేమా? So in the last class we studied about 3 types of voids, no, ma, and their contributions, everything, positions, and how they are formed, everything we have studied, ma. So the last void is cubic void. So where this cubic void will be formed, ma? Cheppandi. Cubic void, where it will be formed? Okay, ma? It is formed in square close method or square close packing. Are you able to understand, ma? And what is meant by square close packing? Do you remember, ma? When one atom is placed exactly below one more atom, then this type of packing you can call it as square close packing. So this is where we got this cubical void, no? Clear, no, ma? And here, what is the radius of the atom which I have to place on the void so that I can cover this void? Okay, ma? So here I have this void, no? What is the shape of this void? Cubical void or cube void. So on this void, if I want to place an atom, then what is the radius of that? That radius of the atom is given by RV is equals to 0.732 times of radius of that. And what is meant by RV and what is meant by RA already we have studied, no? RV means radius of that atom which should be placed on the void to cover that void. and area is the radius of the original atoms which is forming that void. That is the condition. Understood, Dhamma? So that's all. About cubic void, this is the only point which you should remember. Okay? Make a note up to here. Sima. So question is, atom of element B, it is forming FCC lattices, and element A is occupying 2/3 of tetrahedral voids. Clear, Nama? And atom C is occupying 3/4 of octahedral voids. Then what is the formula of this compound? This is the question. Okay, ma? So previously also we have done some problems based on what is the formula of the compound, Nama? There, do you remember what is the method we have adopted, ma, to calculate formula of the compound? Now, ratio of what? Ratio of different atoms of what? Ratio of number of atoms by mass. That's what we have taken, no? Ratio of number of atoms by mass which are present at different positions. Okay? That ratio itself will give the ratio of the element. That's what we have studied, no? For example, if you take the atoms which are present on corners. How many atoms are present at corners? 8. Then what is its contribution? 1. Are you able to understand? Because 1/8 into 8 is 1. Because contribution is 1/8, no? So 1/8 into 1 is 1. So if all the atoms, if they are present at the corners, it means actually one atom is present inside that particular unit cell. That's what we discussed, no? If atoms, if they are present at the centers of phases, then, for example, if one atom is present at center of the phase, then what is its contribution to that particular unit cell? 1 by? I am saying phase center. Phase center. 1/2 is the contribution. Okay, ma? How many phases will be there? 6 phases. So 6 into 1/2? 3. It means that unit cell is enclosing 3 atoms. Are you able to understand, ma? So the ratio will become 1:8. If atoms are present at the corners, 1 atom is enclosed, no? If atoms are present at the phases, 3 atoms are enclosed. So total 1 plus 3? 1 plus 3 only, na? 1 plus 3? 4. Or you can say the ratio of elements is 1:3. Like this we have taken the ratio, no? Here also same concept. Are you able to understand, no? So let us write that concept once again. So formula of compound depends on number of atoms by mass, okay, ma? enclosed by unit cell. This is the method which we have adopted, no? So here also we will adopt the same method. Okay, ma? So see here, what is the type of lattice given? FCC lattice, face centered cubic lattice. Understood, ma? And who is present at FCC lattices, ma? B. Element B is present. Okay, so therefore listen very carefully, ma. Then you can write down. First listen. So B element is present. Are you able to understand? So in B element, where it is present in FCC. Now can you say, if all the elements, if they are present on FCC, then this unit cell is enclosing how many atoms of B? Can you say? 4. How you got this 4? 4 ఎలా వచ్చింది చెప్పండి? In this total FCC lattice, it is equivalent as if this FCC is enclosing 4 atoms of element B. How can I say it is 4? గుర్తుందా ఏదన్నా? Yes. So at the corners there are 8 atoms. No? What is meant by FCC? 8 atoms are present at the corners. 6 atoms they are present at the faces. That is meant by FCC lattice. No? So therefore total contribution is how much? 1/8 into 8 plus 1/2 into 6. That's all, no? Because when they are present on the face, then its contribution is only 50% to that particular unit cell. Already discussed cheskunnam manam. So therefore 1 plus 3 is how much, ma? 4. So it means that this particular unit cell is enclosing how many atoms of element B, ma? 4 atoms it is enclosing by mass. Up to here it is clear, no? Then you see element A. Element A is occupying 2/3 of tetrahedral voids. Okay, ma? So A element or atom of element A, here also FCC only. Are you able to understand, ma? And how many voids it is covering, ma? 2/3 of tetrahedral voids. Okay. Now in a third of 8 is how much, ma? 2/3 of 8, let it be 16 divided by 3. So these are the tetrahedral voids present in FCC. Are you able to understand, ma? So therefore 16/3 atoms are enclosed by this particular unit cell. That is the meaning of this one. No? Are you able to understand, ma? And B element, which is the last element, ma? C element. Atoms of a C element, it is enclosing how many voids? 3/4 of octahedral voids. Are you able to understand, ma? So in FCC only, how many octahedral voids will be present? Octahedral voids. In FCC, octahedral voids, ma? 4. Octahedral voids. FCC octahedral, 4 only, correct. Okay, ma? So 3/4 of 4. That's all, no? So octahedral voids in FCC, they are 4, and they are 6 in HCP, hexagonal close packing. 4 is correct. Clear, ma? So total how many? 3. Okay. Now you take the ratio of ABC. Ratio of ABC is nothing but formula of the compound. Clear, ma? So therefore, A is to B is to C is how much? So which is the first one, ma? A I will take 16/3. You can take B is to A is to C, also anything you can take, no problem. 16/3, A, B. B is 4. And what about C, ma? C is 3. Correct only, na, what we are doing. So if you do this calculation by 9, so 16 is to 12 is to 9. Clear, na, ma? History లెక్కలు కూడా చేయలేకపోతే ఎట్రా మీరు? ఓకే, సీమా. సో ఇన్ ఏ సాలిడ్ అంటే వీళ్ళ తప్పు కాదు, ఇంతకుముందు వీళ్ళకి టీచ్ చేసినట్టు లెక్చరర్లు అద్భుతమైన టీచర్స్ అంతా కెమిస్ట్రీ. ఆ దరిద్రం వద్దని నేనే చెప్తా ఉన్నా, అది విషయం. ఓకేమా? సో ఇన్ అ సాలిడ్ ఆక్సైడ్ ions are arranged in a CCP manner. CCP manner is nothing but FCC, ma, phase cubic central atom. Clear, no, ma? So oxide ions means what? O2 minus, no, ma? O2 minus. So they are arranged in which arrangement? In FCC arrangement. CC means closed cubic packing, ma. Closed cubic packing. Are you able to understand? Equivalent to, so in CCP only you will get FCC. Are you able to understand? So O2 minus in FCC. So FCC atom will enclose how many oxygen atoms, can you say? 4. Already we have calculated in the last problem only, no, ma? So total oxide ions, they are forming which structure? Phase central cubic structure it is forming. Are you able to understand, no? It means that in FCC how many O2 minus atoms can be packed? 4 atoms by mass. Already we have calculated, no? Okay. Then you see about cation A. Okay, ma? So this is anion, no? It means 2 cations are required because it is O2 minus. So there is one cation of B atom, there is one more cation of C atom. That's what he gave, no? No, A and B he gave. Okay, whatever it may be. So cation A is occupying which place, ma? It is occupying 1/6 of tetrahedral voids. Understood, no? And how many tetrahedral voids are present in tetrahedral voids in FCC? 8. Clear, no, ma? So 8/6 is how much? 4/3. మొత్తానికి కలిపి చేయాలయ్యా సుబ్బారావు, ఒకదానికి రావచ్చు రాకపోవచ్చు. క్లియర్, నవా? సిమిలర్లీ cation B. Cation B is occupying what? It is occupying 1/3 of octahedral voids. Clear, no? So 1/3 of how many octahedral voids are present in FCC? 4. Clear, no? So therefore what is the ratio again? Again it is 4/3. So therefore take the total ratio. O2 minus is to A is to B is equals to 4 is to 4/3 is to 4/3. Clear, no, ma? So therefore multiply everything by 3. 12 is to 4 is to 4. Okay, ma? And divide everything by 4. So 3 is to 1 is to 1. That is my answer. అసలు ఏమన్నా ఉందా అది మరి? Sima. This is an important table describing about the ratio of cation to ratio of anion. What is meant by ratio of cation to ratio of anion? Already we have discussed previously, no? RV is equals to some value multiplied by RA. Already we have studied, no? Okay, ma? And when this RV can also be written as R plus also, because void is always smaller, no? Void is always smaller. On that void, the atom which you place, that also will be smaller. So the atom which we place on void is taken as cation, positively charged particle. Understood, no? And this is the radius of the anion, you can call it as, or radius of the atom which is forming that particular void. అర్థమవుతున్నాయి కదా ఏ టర్మ్ దేనికి సంబంధించిందో? సో దేర్ ఫోర్ ఐ కెన్ రైట్ దట్ RV divided by RA, this is also equal to R plus divided by R minus. So it will have some range of values, ma. Yesterday we have written some values, no, they were minimum values. Yesterday the values which we have written, they were minimum values, but a range of values can be present. Okay, ma? Arshia sunte nahi tumhe. So range of values means what? There will be one minimum value, there will be one maximum value also. Yesterday we have written values. What are the values we have written? 0.155, 0.225, 0.414, 0.732. These are the values which we have written. Okay. But if you see trigonal void, then the ratio of the cation to ratio of anion, it will be ranging from 0.155 to 0.225. But it cannot be 0.225, less than 0.225. Are you able to understand? Because 0.225 is the void, is the atom which is related to tetrahedral. So on the tetrahedral void, what can be the ratio of the atom which I can place? 0.225 to 0.414. So this is the minimum value and this is the maximum value. Understood, Nama? Similarly, for octahedral, 0.412, next void, which is the next void, cubical void. And for cubical void, which is the minimum value, 0.732. Okay, so you can pack this one up to 0.731, but not 732, because 732 is related to cubical void. Are you able to understand, Noma? So in between these ranges, any atom you can place on these particular voids. That is the meaning of this one. So these ranges you should remember, because in the questions he will ask what is the maximum value of cation and what is the minimum value of cation. Then if you remember this range, then only you can do such type of problems. Okay, minimum range means this one, maximum range means this one. That's it. Okay, and for cubical void it is 0.732 to 1. Are you able to understand, ma? And coordination number, what is meant by coordination number? Already we have studied. Now coordination number means the number of atoms which can be surrounded and which are present at the shortest distance. That is called as coordination number. Okay, for trigonal or triangular voids, what is the coordination number? 3. For tetrahedral, coordination number is 4. Octahedral it is 6, and for cubical it is 8. And those are the examples. Are you able to understand? So make a note of this diagram, then we will do some problems on this ranges, ma. Okay, see, ma. So let us see this question. A solid having formula AB, cation A occupies octahedral void. Okay, ma. So question is given on what? Question is given on octahedral void. Okay, ma. And in octahedral void, what is the range of radius of cation to radius of anion? Range chudandi pustakalo nannu chustareme 0. So range is 0.414 to 0.732. It means this is the minimum value, no? And this is the maximum value. Now see. So if anion B has, okay, ma, and what is this ratio, ma? This ratio is nothing but R plus divided by R minus ratio. Okay, so R plus value is already given. R plus value is R minus value is how much? 241.5 picometers. Okay, then what should be the minimum radius of cation? That's the question, no? Minimum radius I want. It means I can write this relation R plus is equals to some value multiplied by R minus. This is the formula, no? So if R plus should be minimum, because he is asking minimum value of cation, no, ma? So if R plus is minimum, the value here present also should be minimum only. So out of these two, which one shall I select? Minimum and telusu kada? So 0.414. Okay, ma? So just substitute. R plus is equals to 0.414 multiplied by what is the radius of cation, anion, ma? 241.5. So just to do this calculation, that will be the radius of the cation. That's all. అసలు ఏమన్నా ఉందా ఇక్కడ? అంటే మన బుర్రలో కూడా ఏం లేదు అని అర్థం. ఏం లేదు, గుజ్జే లేదు అసలు. ఓకేమా? సో 99.98 picometers. So that is the minimum value of cation that can be placed on this octahedral void. That is the question. Understood, no? Minimum ఇంత రేడియస్ అన్న మీరు ఆ వాయిడ్ పైన పెట్టాలి. ఓకే, okay, Sima. So let us see this question. So predict the coordination number of My atoms in My crystal if ionic radius of M plus and Y plus are 97 picometer and 251 picometer. Okay, ma? So see. So already we have studied that radius of plus is equals to dash of radius of minus. This is what we have studied. So if you get this value, then you can predict it is belonging to which type of void. ఇక్కడ ఏ టైప్ ఆఫ్ వాయిడ్స్ ఉంటాయో ఫస్ట్ మీరు అది ఐడెంటిఫై చేయొచ్చు. అండ్ వెన్ యూ క్యాలిక్యులేట్ ద టైప్ ఆఫ్ వాయిడ్ అండ్ ఫర్ ఎ పర్టికులర్ వాయిడ్ ఆల్రెడీ వీ హ్యావ్ రిటర్న్ ద కోఆర్డినేషన్ numbers. Are you able to understand, ma? So do the calculation. So R plus divided by R minus is how much? R plus value is how much, ma? 97 picometer. R minus value 251 picometer. Okay, picometer will get cancelled. So 97 by 251 is how much, ma? 100 divided by 300 approximately 0.3 something we will get, no? Where is that? 0.3864. 0.3864. Okay. Now you see this is the ratio of cation and anion, which we got, and 0.3864 will lie in which range? It will lie in the range of, lies in the range of what? 0.225 to 0.414. That's all. ఈ రేంజ్లోనే ఉంది కదా అది. Okay, ba? So it is lying in this range, and this range belongs to which void? Tetrahedral void. So that is my answer. Okay, ma? Tetrahedral void. And tetrahedral void coordination number 4. That is my answer. That's all, no? So coordination number will be 4 for this particular crystal.